This will be a brief overview of Kaldor Hicks efficiency, sometimes also referred to as cost-benefit efficiency, and Pareto efficiency concepts within economics using graphs to highlight our understanding of efficiency. A situation is Pareto efficient if and only if the only way to make one person better off is to make another person worse off. It's important to keep in mind the difference between Pareto efficiency and a Pareto improvement. A Pareto improvement is any change that makes someone better off without making anyone else worse off. This is very similar to a Pareto efficient state of the world, but at a Pareto efficient state of the world, you no longer have access to any Pareto improvements. There's no longer any chances for you to make someone better off without making someone else worse off. Kaldor Hicks efficiency is a situation in which the dollar value of social resources is maximized. This is why this is sometimes referred to as cost-benefit efficiency and is often used when making decisions in terms of everyday real-world policies. Similar to Pareto improvements and Pareto efficiency, we got to keep straight Kaldor Hicks efficient states of the world and Kaldor Hicks improvements. A Kaldor Hicks improvement is any change that raises the dollar value of social resources, whereas a Kaldor Hicks efficient state of the world is a situation where there are no longer any Kaldor Hicks improvements to be had. Now let's do our graphical analysis. The first graph that we're going to use is a Venn diagram. Our first Venn diagram will look at efficient states of the world. Almost every state of the world is Pareto efficient. Any change that occurs usually has some negative ramification, even if it's very, very small, for somebody else. So for example, if I like your watch, and I buy your watch, and I value it a great deal, and you don't value it that much, we, within our transaction, have both been made better off by me paying a lot of money for your watch. However, someone out there at some point in time would have asked you for the time of day, but you no longer have that watch. And so they're made worse off just a little bit, and nonetheless, that means that we're at a Pareto efficient state of the world before I buy your watch. Any change within any situation almost always has somebody who you could argue is made slightly worse off. So basically, almost every state of the world should be considered to be Pareto efficient. Pareto efficient states of the world are very large. Kaldor Hicks efficient states of the world, in contrast to this, are actually quite small. If you think about it, if we've maximized all of our social resources, Kaldor Hicks efficient states of the world where we've already maximized these social resources, that's probably just a small subset of the situations where we have Pareto efficient states of the world. We know that there's plenty of gains to be had from exchange that will increase the value of social resources just by observing everyday life and seeing that, well, people get made better off through exchange and through changing the current state of the world. The same logic here holds for our next Venn diagram where we look at improvements. There are tons of Kaldor Hicks improvements going on all of the time. We see plenty of exchanges that we feel increase the value of social resources. Almost all exchanges and changes can be argued, if they're increasing our value, to be Kaldor Hicks improvements. However, returning back to our watch example, very few of these improvements are Pareto improvements. Often these improvements have some, what could be argued, small negative effect on at least one person somewhere out in the world, and thus that improvement is not a Pareto improvement. So there's very few Pareto improvements to be had. There's plenty of Kaldor Hicks improvements to be had. The next model we'll look at will be a Cartesian coordinate comparison. Here we have a Cartesian coordinate system, and we say that the x-axis is showing our utility of one person, and we're going to be starting at this origin, this 0, 0 origin. So person on the x-axis increases in utility as we move to the right, decreases in utility as we move to the left, and then our other person will be on the y-axis and will increase in utility as we move up, and we will decrease in utility as we move to the south. So here is our original state. First, what we can do is we can look at the idea of Pareto improvements. A Pareto improvement is a situation where at least one person is made better off. So if we're starting at this origin, we could hold person on the y-axis, the north and south, constant. So let's just stay right along the x-axis here. If we move to the right, we see that we are making this first person on the x-axis better off without harming the second person on the y-axis. Therefore, we can see this area right along the curve in the green here would make sense to be Pareto improvements. Eventually, we'll get to a point where we run out of resources and we'll have to stop, but we're having Pareto improvements in that direction. Also, we could hold the person on the x-axis constant, and we could increase the value or the utility of the second person on the y-axis. So we're not going to move from this spot. We're going to keep the person on the x-axis's utility constant. But if we moved up, we could see that we would be making one person, the person on the y-axis, better off without harming the person on the x-axis. So moving in this direction, also in that green area, would make us see that we have Pareto improvements up until a point where we can no longer exchange or move around the goods that we currently have. And obviously, any area in between these two extremes, all of this green area would be Pareto improvements, because we would actually, from the origin, be making both people better off at all of these different points inside the triangle. We're at least making one person better off for all of these areas in the green without harming another person. So the green area is the area of Pareto improvements. The blue area is the area of Kaldor Hicks improvements. What we say is that while from the origin we made the person on the x-axis slightly worse off, but if we make the person on the y-axis slightly more better off than how much we've harmed person X, then we have a Kaldor Hicks improvement, because there's only two people within this world, so we're maximizing social resources if we increase slightly more than what we've decreased. So if we decrease utility of X, the person on the x-axis a little bit, and increase on the y-axis at least as much as, then we have this Kaldor Hicks improvement where we've made the value of social resources higher. And we can see that that would basically exist all the way around anywhere on this axis. And then we could do the same the other way. If we make the person on the y-axis slightly worse off, but the person on the x-axis slightly better off, we would move to a point where the person on the x-axis is better off and we're somewhere in the blue. We could do that for all of these areas in through the blue, and also the area of green would also be a Kaldor Hicks improvement, because both people would be made better off, and thus obviously we've increased the value of social resources there as well. Once we hit the red line here, we've basically gone as far as we can in terms of efficiency. So we're at efficient states of the world. Right, so while we're along the red line, we're at Kaldor Hicks efficiency or Pareto efficiency once we've moved to that state of the world.